Okay, hi everyone, thanks for having me. I'm Matt, I'm a PhD student at the University of Birmingham, but right now I'm in Milan. And today I'm going to talk to you about some applications of deep learning techniques in the population inference problem 2, specifically tackling whether we can identify the presence of repeated black hole mergers in the current catalogue. So the question we want to answer ultimately is, where are the merging stellar mass binary black holes detected by Virgo born? Where do they come from? And there's been lots of proposed channels, so traditional isolated binary stellar evolution, more exotic channels such as primordial black holes, and also dynamical environments, so mergers of black holes in things like stellar clusters or the disks of active galactic nuclei. And if you look at the predictions of all of these different models, what you find is that within some uncertainties, pretty much all of them are consistent with the rate observed by LIGO Virgo. So how do we detect which of these formation channels are likely contributing to the merger rate? And in particular, I'm going to focus on these dynamical channels of star clusters. And these are kind of promising contributions to the merger rate because we've seen in the current LIGO Virgo catalogues evidence for masses which are higher than you expect from traditional binary isolated stellar evolutions. And they have some events like 1905-21, as well as having high masses, have spins which are tilted with respect to the orbital angular momentum. And these kinds of properties, these mass and spin properties, are naturally produced in dynamical environments in which binary black holes interact with other members of clusters, and those dynamical interactions act to randomize the spin orientations, but also the remnants of previous mergers can then interact with other black holes to form a new binary and then to merge again, and this naturally leads to larger masses. And different star clusters, especially nuclear star clusters, are pretty efficient at retaining merger products, because once a binary undergoes a merger, it receives a gravitational kick. So due to the fact that gravitational waves aren't emitted uniformly in all directions, there's some velocity boost in a given direction post-merger for the remnant black hole. And nuclear star clusters can retain up to about 50% of merger remnants. If the gravitational kick velocity, if its magnitude exceeds the escape speed of the host environment, then it's going to be ejected from the cluster and not merge again. So how can we go about modeling this repeated merger scenario? So we construct a simplified simulation scenario. We perform 1,000 simulations, each of which consists of 500 clusters whose escape speeds are drawn from a power distribution. And in each of those clusters, we generate 5,000 seed black holes from a power law mass function with some upper cutoff, and the spins are generated uniformly in magnitude and in direction, again with some upper cutoff in the spin magnitudes. And then we pair individual black holes into binaries with some power law pairing probabilities. So these 6 parameters I've highlighted in green are 6 key parameters that we're going to target and try to constrain with a population inference. Now, to compute the remnants of binary mergers, we use some numerical relativity fitting formulae. And crucially, this allows us to compute the mass and spin magnitudes, which we retain, and also the kick velocity. And so if that kick is less than the escape speed, the merger product is retained in the cluster and it can go on to merge again. And so this parametric model of binary black holes is transformed into complex numerical distributions through the presence of this remnant retention and repeated mergers. And this is the result of some example simulations. What we can do is split up the population into the first generation components, and then the components which have undergone multiple mergers. So second generation black holes are those which have already merged once, and then there could even be black holes which have undergone more than 2 mergers in the population. And you see that the distribution of the source parameters, so we model the Chirp mass, the mass ratio, the effective aligned spin, and the effective processing spin, where we use a new definition which accounts crucially for both black hole spins. These distributions change a lot depending on those 6 input parameters I mentioned before. But importantly, the repeated merger scenarios have key features such as multiple peaks in the mass and spin distributions, which we can use to identify the presence of hierarchical mergers. Now, in order to constrain the population, we have simulations performed at a finite number of points in the parameter space. So we want to construct an emulator which can accurately model those simulations in a continuous fashion. So here's where we use some deep learning techniques. For the population model, we start by, for each simulation, generating a bunch of samples using kernel density estimation. So we have a bunch of samples approximating the population density at many points in the parameter space. And then we learn the full mapping of the combined vector of the source parameters theta and the population level parameters lambda with a deep neural network. And this is the structure of the network for those who are interested. So we have a neural network which takes a 10-dimensional input and spits out a value of the normalized conditional density p-pop. And this neural network is quite large. It takes about 200 million samples to train, which takes a few days on a single GPU core. Now, another ingredient which we just heard about in the last talk, which you crucially need to account for in population inference, is the selection function. So for each merger in each of our simulations, we estimate the detection probability with a semi-analytic approximate, and then we compute the values of the selection function for each simulation. So we then use a deep neural network to learn this function continuously across the parameter space. And this is a much smaller network because it's only a function of the 6 population level parameters, and there's only a 1,000 training points. And we use deep learning techniques in a final situation, which is to emulate the branching fractions between the different merger generations. So we have these 4 labels where the binaries consist of 2 first-generation components, or a mixed generation, 2 second-generation components, or whether they contain a black hole which has undergone 2 mergers or more. And again, we have a deep neural network to learn this mapping. The only difference from the previous one is that there's now 4 outputs corresponding to each of these labels, and the predictions must sum to 1, so the branching fractions have to sum to unity. So now we combine all of these ingredients and we perform a population inference on the mergers detected, the binary black hole mergers in GWTC3, the third gravitational wave transient catalog. So I'll start with our constraints on the escape speeds of host environments. So with this power law, we find a negative slope, which implies a preference for lower escape speeds, which we see in this blue peaked distribution. Although this distribution is consistent with a uniform distribution within the 90% credible range. Now we can compare this to the distribution of gravitational kicks received by first generation sources, and we find that a good fraction, about 40%, will be retained in their host environments, which means that we're going to see high generation mergers, high generation black holes present in the population. So what's the effect of that on the mass distribution? So here we present our constraints on the mass distribution, where I'm comparing again the first generation distribution of masses with the full distribution of all masses, both primary and secondary. And what we find is that there is an extended spectrum of masses above the first generation cutoff, which is given by this Mmax, this shaded credible region. And this cannot be accounted for by the first generation sources. And we find that most sources lie in this range up to about 60 solar masses, but this upper cutoff, which we find to lie about 40 solar masses, this is consistent with the predictions made by the theory of stellar evolution and supernovae. So now onto our spin constraints. I'll just remind you, we modeled first generation spins as uniform with some upper cutoff Chimax, and we can place a constraint for this parameter around 0.4. The spins, however, were modeled isotropically, and this leads to a strict constraint on the shape of the effective spin distribution. It's enforced to be symmetric due to this assumption of isotropy, which isn't consistent with other analyses which have shown a preference for positive chi-f, or indeed ruling out negative chi-effective entirely. But this is just part of it's kind of a misspecification in our model. But what we do find consistent with previous analyses is that the magnitudes of chi-f. So we typically find that black holes in the current catalog have, and in the underlying population, have effective spins less than about 0.4. More interestingly, we can look at the constraints on the processing spin. And here we find a multimodal distribution. So there's two peaks, one at about 0.2 and one at about 0.6. And we verify that this chi-p equals 0.6 peak is in fact due to repeated mergers. And unlike the previous LIGO-Virgo analyses, we find that to model these two peaks, you have to model them simultaneously. So if you try to model these with something like a Gaussian, you can only model one at a time, whereas our model naturally accounts for both peaks together. And indeed, this 90% credible region is inconsistent with a single Gaussian.
Just to let you know, Matthew, that's 10 minutes now. So
okay, thank you. So just to quickly finish off, we can look at if there's any constraints on two-spin effects, and we find that only less than 1% of sources modify this exclusive two-spin region, which presents in our new chi-p parameter. And the final result I can share is that given our neural network to interpolate the branching fractions, we find that at least 15% of the sources in the underlying population have a component which has undergone a previous merger. So I'll just leave up my summary here. And thanks for listening, and I'll take any questions.
Thank you very much, Matthew. That's really interesting. So let's just have a look at the questions. So I can't see any just now. So I'll just try and think of a question. I think I have one written down somewhere. So you said it takes a few days to train this. Is that like? Is there any way you could sort of reduce that time? Do you have any ideas of how that?
The key cost for training the population model, which is the expensive one, is the number of samples. So we have 1,000 simulations, and the training samples consist of about 200,000 evaluations of the density estimates per simulation. So we have about 200 million training samples. But really, you need this many to get a good learning for this 10-dimensional mapping. So there's not really any way you can reduce that from that standpoint. You could train on multiple GPUs. You can, and that would reduce your cost in terms of time, but it still has the same computational requirements. The other neural networks, so the ones interpolating the selection function and the ones interpolating the branching fractions, these are much smaller models, and you can train these on your laptop in a few minutes.
Okay, that's interesting. Thank you very much. I think we have another question as well, which is, do you have plans to expand on the selection function treatment from the semi-analytic approximation, for instance, with the injection runs?
Yeah, so in principle, you could use injections to interpolate your selection function, but in previous population studies based on GWTC2, at least we found that we could completely reproduce the results where injections were used to compute the selection function just with this semi-analytic approximate. So it seems like the more expensive generative process of performing injections isn't entirely necessary to get an accurate estimation of this selection bias.